Hi, and welcome back to my channel. Today I'm going to be doing a COMSOL tutorial, and let's see what we're going to do. So I just go to the COMSOL application gallery, filter by COMSOL multiphysics, and I'm just sort of going in order here. So here's all the ones we've done already. Second page I think is where I left off. I just did that one. Alright, diffraction patterns. Let's take a look. So this example resembles the well-known double-slit interference experiment often demonstrated in schools with water waves or sound. Okay, this is interesting. Dealing with wave theory. The model mimics the plane wave excitation with two thin waveguides leading to slits in a screen and computes the diffraction pattern on the opposite side of the screen. The diffraction pattern is clearly visible. The main effect of discretization is that the numerical wavelength differs from the wavelength lambda, and thus results in a systematic shift in the angles. It's possible to correct for this effect by adjusting the value of k in the Helmholtz equation to the element size. Such practices are important when you wish to briefly model interference effects of monochromatic waves. Alright, so let's download the application files. Oh, this one looks easy. We only have 2 files. So let's go straight away to the PDF. So basically when you observe the wave passing through, it behaves as a particle. But if you don't observe it, the result is that it behaved like a wave. So it's demonstrating the wave and particle behavior, the simultaneous wave and particle behavior with the slit experiment. So the theory predicts amplitude minima along rays where the difference in travel distance is an odd multiple of half the wavelength, and maxima at even multiples for n equals 0, plus or minus 1, plus or minus 2, etc. Theory says that the minimum happens at this interval, sine theta equals n plus 1/2 of lambda, the wavelength, over d, where d is the distance between the two slits, which is 2 lambda. And the maxima occur at sine, on the interval sine of theta, for n, where n is every interval, 1, 2, 3, etc., times lambda over d. In this example, the distance d between the slits is 2 lambda. Maxima should then be found at theta equals 0 and 30 degrees, while minima should appear at theta equals 14.48 and 48.59 degrees. So here's our governing equation, the Helmholtz equation, for time harmonic propagation. So this is a simplification of the wave equation. We've got negative del of del u minus k squared u equals 0, where k equals 2 pi over lambda. So we've got a, second order. On the inflow and outflow boundaries, absorbing boundary conditions apply. Let's briefly show how the conditions in their simplest form can be derived. So first, assume the solution of the boundaries to be the sum of an incident wave, plane wave, un, propagating in an arbitrary direction, and a scattered wave, u scattered, propagating in the normal direction. So we have contributions from both of these terms making up the entire u expression, the entire wave The entire wave equation takes into account contributions from the incident plane wave, un, and the scattered wave, usc, which equals u naught e to the negative I k times x vectors plus us times e to the negative I k n times x. Here, n vector is the outward boundary normal vector, and k equals the absolute value of the k vector. the boundary of the modeling domain gamma, we then have del u evaluated at gamma at the boundary of the modeling domain equals negative I times k vector times u naught times e to the power of negative I times k vector times x vector minus I times the absolute value of k times n vector times u sub s times e to the power of negative ik times n vector times x vector equals negative I times the absolute value of the k vector times the normal vector times u evaluated at gamma minus I times u naught times quantity k vector minus absolute value of k times n vector times e to the negative I times k vector times x vector, where equation 1 was used in second step. So we've done direct substitution for un plus usc and evaluating the Helmholtz equation, and you end up with equation 2. It then follows that equation 3 is true. The normal vector times del u evaluated at gamma, the boundary of the modeling domain, equals let's see, the negative imaginary component of the absolute value of, what is k? Let's k, the wave number. Alright, well, anyway, I think k in the Helmholtz equation is the wave number, so I'm just going to keep going. Alright, so anyway, negative I times the wave number plus u defined at the boundary plus the positive imaginary component times u naught being the incident plane wave part of that expression, times quantity wave number minus normal vector times okay, so they don't explicitly define it here, but just judging by the context and further explanation down here, it looks like k vector describes the inward normal direction and n vector is the outward boundary normal vector. So they're basically opposite. Okay, well, this is getting a little confusing to attribute physical meaning to each of these terms because we're talking about a wave equation, which doesn't necessarily have physical implications that you can relate to every term because it involves phase and imaginary numbers. So just take this at face value for now. If you want to dig into the mathematics, then you can do that, but we're just going to focus on the modeling today. Okay, so then we end up with conditions in equation 4 for inflow and outflow conditions. And in this model, these conditions are readily imposed using the coefficient form PDE interface's flux source condition. Default condition, 0 flux, applies on the remaining boundaries. Anyway, here are the results we will generate. So we're going to create a diffraction pattern in the simulated double-slit experiment, where you can see the input, what do you call it? Inflow, incident plane waves. So in figure 2, you can see the incident plane wave through each of the two slits, and then the wave comes out and travels with time. And the same side here, so you've got interference happening. It looks like red is constructive interference, and blue would be where the destructive interference is happening. So you've got the white lines here, where you have 0 as the value of u. Alright, so the result is that you have 4 pings over here on the wall, your observation wall. If this were a pool with water flowing through, then you'd have 4 places where there's 0 impact. Or if this were light, then these would be your dark spaces. Alright, so let's start with our model wizard. Model wizard, 2D model, and we're going to use this is going to be a mathematical study, not a physics study. So we're going to mathematics, PDE interfaces, add and study, and then we're going to do a stationary study. So if you wanted to do an eigenvalue study, you could compute the eigenvalues and eigenmodes of a linear or linearized model in a generic eigenvalue formulation where the eigenvalues are not necessarily frequencies. This is typically used for equation-based modeling. We're going to do a stationary study when the field variables do not change over time. It gives you some examples here. In fluid flow, it's used to compute the steady flow and pressure fields. So that seems appropriate since we have a steady incidence flow. Alright, so let's go ahead and put in our global definitions parameters. Actually, let's save first. Diffraction patterns. Save, and then we're going to enter these parameters into the table. So L, or lambda, is the wavelength. K is the wave number. Okay, good, I was right. It's the wave number. Is 2 pi in radians over the wavelength. And U naught is the value of 1, which is the incident wave amplitude at inflow boundaries. So we have a normalized wave amplitude here. Alright, now we're ready for geometry. So first we're going to add a circle from the geometry toolbar here. And then under size and shape and the circle settings, we're going to go to sector, angle, text field, and type 180. And in the position, X is going to have a coordinate of 0.5, and then locate the rotation angle section. And we're going to put -90. Build selected. Alright, there you go. So we have 180 sector angles with semicircle of radius 1. So you've got a diameter of 1 to -1, because the center is at y equals 0. But as you see, the center is 0.5 offset on the x-axis. And we also have a rotation of -90. So just to see what it would look like without that, if we had 0 rotation, it would look like a semicircle in this direction. So the rotation will be in the clockwise direction. So if we say rotate it by -90, that means a quarter turn downward to the right. Alright, now we're going to add a rectangle. And this rectangle is going to have a width of 0.5 meters and a height of 0.03, 3 centimeters tall. And then for our position in the y text field, type negative 0.015 minus 0.1. What? Why would they write it like that? Okay, build selected. Okay, so this is telling us to do it from transforms. In the geometry toolbar, click on transforms, copy, rectangle 1 is selected, and then in the settings window for copy, locate the displacement section. So we've got to highlight our input objects. So we have a green here with R1 selected. Displacement is going to have a y displacement of 0.2 meters. That's build selected. So we have another rectangle, a similar rectangle displaced positive 0.2 meters on the y-axis. Now we're going to build a union. So let's go to Booleans and partitions, choose union, Control Alt, select all objects, and then in the settings window for union, locate the union section, clear the keep interior boundaries box. So we don't want the boundaries and the slits, we want those to be free flowing, and then build all objects. So now we have one continuous geometry. Alright, now we're ready to input our coefficient form PDE settings, our boundary conditions, flux source conditions, and that's it, yeah. Okay, so in the model builder window, under component 1, coefficient form PDE, click coefficient form PDE 1. And in the settings window, we're going to locate the absorption coefficient section and type negative k squared. It's the wave number squared for the absorption coefficient A. And in the source term, we're going to put 0 for F. Proceed to apply the boundary conditions, equation 4, at the inflow and outflow boundaries. Alright, so now we're ready for our flux source 1 condition. In the physics toolbar, click boundaries, physics, boundaries, and choose flux source. Select boundaries 1 and 4 only. So that is our inflow at the beginning of each of the 2 slits. And in the settings, we're going to go to the boundary flux source and type our expression negative I times k times u plus 2 times u naught times I times k times exponent of negative I times k times x. Alright, note that the phase factor expression evaluates to 1 because x equals 0. It has been included nevertheless for completeness. Okay, so at this particular point, x equals 0, so if we were to plug that in, we have exponent of 0 is just 1, and then you've got a negative I term plus this term times 1. Alright, and then we're going to add another flux source condition from boundaries under the physics toolbar. And now we're going to select boundaries 11 and 12. Let's see. So where the wall is hitting, or where the wave is hitting on the other side of the wall. And then in the settings for the G-text field, we're going to type expression negative I times k times u Alright, now we're going to create a free triangular mesh. So create a mesh with a maximum element size determined by the wavelength. As a rule of thumb, you need 5 elements per wavelength for quadratic elements, the default for the PDE interface, to fully resolve the wave. In the mesh toolbar, click free triangular. So we're going to go to mesh and click free triangular, and then in the model builder window, click size. So we're not adding a size, we're going to the default size nested at the same hierarchy as free triangular. Click the custom button, in the settings window for size, locate the element size section, click the custom button, and the maximum element size text field, type 1/5. So this is using their rule of thumb that you need 5 elements per wavelength. So if we're saying 1/5 meter is the maximum element size, and our wavelength, if you recall from the parameters, we had our wavelength lambda is 0.1 meters. That doesn't make sense. We're going to do build all. That cannot be right. I don't want to be too heavy-handed, but I think there's a mistake in this tutorial, because based on the rule of thumb that they just gave us, we need 5 elements per wavelength for quadratic elements, and our wavelength that we define, lambda, is 0.1 meters. That means we need, so if you do your dimensional analysis, this comes out to 1/50th meter is the maximum element size. It's a much smaller element size than 1/5 meter. If you do 1/5 meter, you get this. That does not look like this, right? You're gonna get crap resolution with 272 domain elements. So I don't know what went wrong here. Maybe it's a version change artifact, but it should be 1/50, not 1/5. Anyway, here's your resulting mesh, and in the home toolbar, click compute. So we're going to click on study and compute. This one's pretty short and simple. Alright, so to reproduce the plot shown in figure 2, just change the color table. In the model builder window, expand the 2D plot group 1 node down here and click on surface 1. Then we're going to go to coloring and style and choose wave light from the color table list. So it gives you red and blue. It's a little more aesthetically pleasing, or at least easier on the eye to look at than neon green and yellow, for this purpose anyway. And there you go. So let's see, did we say at the beginning, are we looking at light, or it could be water waves or sound? Alright, so let's say if this is sound, and I don't know, your source is 2 speakers emitting through 2 slits with soundproofing on either side of the slit into a theater. Say this is an amphitheater. Then the people sitting at these 4 intervals will have the worst sound. They won't be getting any of the constructive interference. So you might make these aisles if you were doing sound design of an amphitheater. If you're talking instead about water, This could be a wave pool, let's see, and you've got your source of waves, the power generator over here, your motor pushing water through these slits, and then it's coming out into the wave pool. So anyone on these 4 trajectories will not be impacted by the waves because you have a magnitude of 0 on our surface plot of the dependent variable u. And remember, u is our total wave equation that takes into account the incident wave and the scattered wave. U equals un plus USC. So the resulting wave pattern is the contribution of the incident wave coming from the source and the scattered wave destructive or constructive interference. If you like this video, please hit like and feel free to comment and share with a friend. Even if you don't really want to share with someone, you can just hit the share button underneath this video and hit copy link. The algorithm can't tell the difference, and it really helps to get my video out there. So thank you so much for watching, and I'll see you in the next video.